Salam alaikum. Today we will see biomedical spectroscopy. This is the last chapter for optical monitoring and treatment course. In this section, we will see the basic concept of spectroscopy and the different kinds of spectroscopic techniques. Then specifically we will see the ultraviolet visual infrared visual spectrum spectroscopy and the infrared spectroscopy, and Raman spectroscopy techniques and the instrumentation associated with each spectroscopic techniques. First, let's start with a definition of spectroscopy. Spectroscopy it is a study of interaction between matter and electromagnetic radiation, either through electron spectroscopy or atomic spectroscopy technique. Historically, spectroscopy originated through the study of visible light that dispersed according to its wavelengths by a prism. It comes from two words, which are spectron and ghost, or spoken is to see, and the spectron means a ghost. So with light, you are not looking directly the object or the molecule or the matter, but you are looking the ghost, because we perceive objectives, we understand objectives when light interacts with them, and we see only the reflected light. In that case, we are not directly looking the object. There is no way of looking the object directly, but the ghost or the captured light, according to the different wavelengths and reflected intensity, will be acquired by our eyes. So you observe the light interaction with different degree of freedom, not the object directly. So each type of spectroscopy differs with light frequency, and that gives a different picture, which is called spectrum. So spectroscopy, it is a technique of splitting, or more precisely, electromagnetic radiation into its constituent wavelengths, which is called a spectrum. It is in much the same way as a prism splits light into different rainbow of colors. However, in general, spectrum is generally more than simple rainbow of colors. It is a general methodology that can be adapted in many ways to extract information you need, specifically the energies of electronic, vibrational, rotational states, and the structure and symmetry of molecules. The dynamic information can be acquired. The goal of spectroscopy technique is to understand how light interacts with matter and how to use this to quantitatively understand the sample. It helps also understand common tools of measurement like watch or a ruler. It helps us also understand see things or tools that you can put together in different ways to understand systems, and helps us to solve some kind of chemical problems. So the energy levels of electrons in atoms and molecules are quantized, and the absorption and emission of electromagnetic radiation only occurs at specific wavelengths. Consequently, spectra are not smooth, but it is just punctuated by lines of absorption and emission that provides us to identify different objects with respect to different absorption frequency and emission frequency. So in its most basic form, spectroscopy or spectrometer consists of an opaque barrier with a slit in it, like to form a narrow beam of light, and a prism is also required to split the beam into its component colors, and either a detector or a screen is required to allow the user to view the resulting spectrum. So spectroscopy or spectrography are terms used to refer to the measurement of radiation intensity as a function of wavelength, and they are also often used to describe experimental spectroscopic method. So the spectral measurement devices, they are also referred to as spectrometers or spectrophotometers or spectrographs or spectral analyzers. So spectrometer is an instrument which is used to measure and record light waves over part of the electromagnetic spectrum or the line spectra, and it helps us determine the line spectrum of various light sources, materials, or elements. So the spectrometer is also a tool which is used to examine which parts of light are absorbed by different materials. So spectroscopy, it is a process or a procedure, whereas spectrometer is an instrument that helps to see objects through these spectroscopic techniques. So the basic concept for this spectroscopic technique is energy transition in a molecule. As you know from your previous classes, when light gets absorbed, the electron that absorbs that light could be ejected to a higher state, which is excited state, and upon returning to the ground state, it could emit light with different wavelengths. So the absorbed light may not be directly used to emit the electron or to emit another light, but energy could be lost due to some kind of non-radiative intern conversion or non-radiative loss, or as an example, heat. And that energy is equivalent to the frequency of the absorbed light. The frequency of the absorbed light. And this photon should have the energy which is equivalent to or greater than the energy gap of two energy states of a molecule. So optical spectroscopies measure transition between energy states of a molecule. So we specifically measure the transition between energy states of a molecule. By doing that, we can be able to see different frequencies or different emitted frequencies or different absorption frequencies. So most importantly, the absorption and the emission property of a molecule are very important, and that can be used as a fingerprint to identify different kinds of molecules. In its advanced form, when an electron in a molecule with a singlet or ground state is excited through absorption of radiation to a higher energy level, either an excited singlet state or excited triplet state will form. We have said that there are different energy states, excited energy states in a molecule. Those are singlet state and the triplet state. A singlet state is the molecular electronic state such that all electrons spin are paired. Electrons have a spin, and that spin has a direction, either upward or downward. So in the case of singlet state, a molecular electronic state, the spins or the electron spins are paired. So a molecule exists in a triplet state when its total spin, or which is called angular momentum or quantum number, is equals to 1. That means either the molecule could have an additional spin, and the total spin or angular momentum is equivalent to 1. This is called a triplet state. So in the excited state, an electron could be either in the triplet state or in the singlet state. So there are different procedures. When an electron absorbs a photon, different procedures could occur. The first procedure is absorption. So absorption of incident radiation promotes the molecule to an excited electronic state. It is also possible to excite the molecule to a higher vibrational and rotational levels within the excited electron state, so that there are many possible absorption transitions. A single or singlet state, or first singlet state, second singlet state, or third singlet state, you can continue that way. And in a single singlet state, there could be different vibrational or rotational levels. This is, for example, one rotational level. This is another rotational level. This is another, vibrational levels. This is another vibrational levels. So when an electron is excited to a higher state, it could be at this point, which is one vibrational state, or it could be at this point, which is another vibrational state. So there is an energy difference between this vibrational state and this vibrational state. So absorption of incident photon promotes the molecule to an excited electronic state, and it's possible to excite the molecule to higher vibrational and rotational levels within excited electronic state. So there are many possible absorption transition within the excited molecules. The other process is called the internal conversion. The internal conversion is the process in which an electronic crosses over to another electronic state of the same spin multiplicity. That means singlet to a singlet, or triplet to another triplet. So systems excited to a higher energy vibrational and rotational status also lose their extra energy as a heat. So the internal conversion is a process in which an electron crosses over to another electronic state. It is a transition from one excited state to another excited state of the same multiplicity, spin multiplicity, either singlet to singlet or triplet to triplet. This is called internal conversion. The other is emission. So emission of a photon from a singlet excited state to a singlet ground state, or between any two energy levels within the same spin, it is called fluorescence. So the possibility of fluorescence is very high, and the average lifetime of an electron in the excited state is only 10 to the power of -5 up to 10 to the power of -8 seconds. There are two procedures in this emission. Either the electron could be emitted or could return to the ground state through non-radiative process or through emission, which is called fluorescence. In the case of non-radiative transition, the electron will lose its energy in the form of heat, not light. But in the case of fluorescence, the electron will lose its energy in the form of light. The other procedure is called the intersystem crossing. Intersystem crossing involves a spin flip of the excited state electron. That means it is a transition from a singlet state to a triplet state. This is called a forbidden transition. So in this state, electron will transit or cross from a singlet state to a triplet state. That means there will be a spin flip of the excited state electron. The electron could be in this spin. When it changes its spin, flips its spin, and it comes to another state, it is called triplet state transition or intersystem crossing. The other is called phosphorescence. Phosphorescence, it is the forbidden process, which is a transition of electron from the triplet state to the ground state. This is called phosphorescence. It occurs for a system in triplet state to emit a photon of radiation, and theoretically it is a forbidden process. It does not happen for some molecules, and this emission is known as phosphorescence. So there are two common occasions where you have likely seen the phosphorescence emission in your day-to-day life. One is from a glow in the dark stickers. You may have seen stickers that glow in the dark. That glow comes from the phosphorescence process. The other is if you have ever turned off your television in a dark room and observed the screen has glow that takes a few seconds to die down, that's called also phosphorescence. So phosphorescence is usually a weak emission from most substances. So an electron that is excited to excited state by absorbing a photon can undergo different processes, either internal conversion or intersystem crossing or phosphorescence or emission through non-radiative process or emission through fluorescence. These are the possible transitions for an electron that is excited to a higher energy state. So what does a spectrum measure? We have said that the spectroscopy measures the energy transitions when an electron emits or absorbs light. So the interaction of light with a sample can influence the sample or the light. So in the case of spectroscopy, we are interested to analyze a sample. That sample is full of molecules, and we are interested either to measure the concentration of that molecule or to identify the molecular structure of that fluid or liquid. So there are two methods to identify either the concentration or the molecular structure or the fingerprint of molecules. So these methods involve either excitation and detection. Excitation and detection. So the basic idea is light will be applied to the sample, and then we characterize the light after the sample and also characterize the change in the sample, which is called photoacoustic specification or photochemistry. So the procedure is, there is a light, white light, there is a spectrum or a prism that is used to disperse the light into different wavelengths, and there is a pinhole or selector that selects a single wavelength light, and that single wavelength light will be applied to a solution. The solution will absorb some amount of that incident light. We measure the transmitted light. We compare the transmitted light, either intensity or frequency, to the incident light intensity or frequency. That helps us characterize the solution. So the difference between the incident and transmitted light, either intensity or frequency, indicates the absorbance. And that absorbance helps us to understand the molecule, because different molecules have a specific absorption frequency or absorption wavelengths and transmittance. So in an excitation spectrum, we have absorption spectrum and emission spectrum. Absorption spectrum is also called excitation spectrum. Because the light that is used can be absorbed in the molecule and can excite that molecule. That's why it's called also excitation spectrum. So in the excitation spectrum, the emission monochromator is set to some wavelengths where the sample is known to emit radiation, and the excitation monochromator is scanned through different wavelengths. So a change in intensity of the incident light will be measured. The sample attenuates light, and the transmission light T can be represented in terms of the ratio of transmitted light intensity divided by incident light intensity. So we measure the absorption of light at different frequency or wavelengths, because every molecule have its own absorption frequency. If a molecule absorbs that specific wavelengths, that means there is that known molecule that absorbs that specific wavelength. So we have the x-axis, I mean the y-axis, which is the amplitude, and we have the x-axis, which is the wavelength or frequency. The wavelength or frequency. So the x-axis characterizes the input light in terms of frequency, wavelength, or energy. If there is a change in wavelength, that means there is a change in frequency. That means there is a change in energy. So the x-axis in the spectrum represents the wavelength or the electromagnetic radiation. The y-axis represents the absorption, which can be represented in terms of the Beer-Lambert's law. Absorption at specific wavelength or frequency is equivalent to minus log of I, the transmitted intensity, divided by the incident intensity of light, which is equivalent to epsilon, the molar excitation coefficient, times frequency, times the concentration of the molecule, times the sample length. The sample length. So this comes from assuming that the fraction of light absorbed as you propagate through the sample is proportional to the distance traversed. The distance traversed, which comes from this equation, di with respect to I is equivalent to minus alpha dx. Minus alpha dx. So this y-axis represents the absorption, and the x-axis most of the time represents the wavelength or wave number. So if a molecule at specific wavelength absorbs much of the light, this could be an indication of a specific molecule or a fingerprint of a specific molecule. So because different molecules have a specific or unique absorption wavelengths, it's possible to identify what kind of molecular composition a sample has from this spectrum. So two types of spectrometers can be used, either the dispersive or the Fourier transform. The dispersive or the Fourier transform. The dispersive measures the change of intensity of light at different frequency as it passes through a sample, which is indicated on this diagram. It measures the change of intensity of light at different frequencies, and that specific detected frequency can be a fingerprint for a specific molecule. In the other case, you can use the Fourier transform. This helps us separate different frequency components. The detected intensity can be converted to a Fourier transform that helps to identify a specific frequency received. So the transmitted frequency helps us understand what specific frequency has been absorbed on the sample. That will help us identify the type of molecule or the intensity of, the concentration of the molecule also. The other method is the emission, which is called emission spectrum. In the emission spectrum, the excitation monochromator is set to some wavelengths known to excite the sample, and the emission monochromator is scanned through different wavelengths. So excitation induces emission of light from the sample, usually of different frequencies, and we scan the emitted light at different frequencies. So this emission spectrum includes fluorescence, which is emission from excited electronic singlet state, or phosphorescence, which is emission from excited electronic triplet state or forbidden state, we may have also Raman scattering, which is light scattering involving vibrational transitions. So the procedure is the same. We have a source, light source, we have a sample. The light source or excitation monochromator will be set to some wavelengths known to excite that specific sample, and we scan the emission monochromator through different wavelengths, or the detector will scan the different wavelengths. We have another method which is called optical rotation. In the optical rotation, also known as polarization rotation or circular birefringence, it is the rotation of the orientation of the plane of polarization about the optical axis of linearly polarized light as it travels through certain materials. So optical activity occurs in chiral materials. That means those lacking microscopic mirror symmetries. For example, our hands doesn't have mirror symmetry. So molecules or objects that doesn't have a mirror symmetry are called chiral materials, and in these chiral materials optical activity can occur. That means when you apply a light of a specific polarization to a sample, the molecule or the optically active solution will change the polarization of the light. That means, for example, in this case, the polarization of the light is vertical. After applying this light to the optically active solution, the polarizability of the light will be horizontal, as you can see. If a molecule changes a specific polarized light to a different polarization, the solution is called optically active solution. So polarimetry, which is using polarimeters, measures the degree of rotation of the polarized light as it passes through an optically active material. So using the polarimetry, we can measure the degree of polarization on the detector side. So since specific molecules have a specific optical rotation or polarizing angle, identifying that polarizing angle for a specific molecule means identifying that specific molecule from the solution. So optical rotation is another method of identifying the molecular structure or the concentration of molecules in a sample. So we have seen three methods. One, the emission spectrum, or the other is the excitation spectrum or absorption spectrum, and the third one is the optical rotation. So using these three basic techniques, optical spectroscopy can be applied to identify the molecular constituent of a sample or the intensity of a sample. There are mainly two kinds of spectroscopy techniques. One is the atomic spectroscopy, the other is the molecular spectroscopy. Why do you think some light sources have different line spectrum or different colors? This is due to the emission spectrum. Atoms of different elements have different electronic structures. Hence, light emitted and absorbed vary from every element when excited. So the emission spectrum of an element is the pattern of light emitted with its own characteristics pattern of frequencies. Therefore, every element has its own specific line spectrum. So by using this spectroscopic technique or spectrometer, we can identify the line spectra of atoms. when the spectrometer splits white light into different colors, the spectrum of all colors of the rainbow is recorded on the photographic plate. The colors we see depend on the frequency of the light waves we see. So when an element, specific element, is heated, it emits light that is unique to the atomic structure of the element. The light emitted is split through the spectrometer to different frequencies of light. This produces a unique line spectra of the element. So specific light frequencies give rise to sharply defined bands on the scale. So this line spectra of light emitted elements is known as the emission spectra for a specific element. Elements can absorb light too, and the absorption spectra of an element can be also identified using a spectrometer. So we have either the emitted line spectra or the absorption line spectra for an element. So the spectrometer is able to identify both the emission and absorption spectra of the element. So every element which exists in the periodic table has its own emission spectra or absorption spectra, and that can be identified by different colors. For example, hydrogen have a red line spectra. Another example, sodium. Sodium has a very characteristic yellow band in its emission spectra and can be seen when tested with sodium vapor lamp on a spectrometer. That helps us identify what kind of element exists in a sample. The other one is the molecular spectroscopy. When atoms combine into molecules, additional energy terms arise from the vibrational and rotational normal modes of the structure. Transition between these states lead to a complex band spectroscopy, which allows a study of the interatomic potential and the elucidation of the chemical bond. So this molecular spectroscopy involves the interaction of electromagnetic radiation with materials in order to produce an absorption pattern, or which is called a spectrum. Then structural or compositional information can be deduced from that molecule. So either from the electronic transition, or the vibration, or the rotation, molecules can absorb light through these different ways, either through the transition or vibration or rotation. Applied light can be absorbed, and through the absorption spectra it's possible to identify the compositional or structural information of a molecule. So molecular spectroscopic methods, they are among the widely used of all instrumental analytical methods. It is used for identification and determination of huge number of inorganic, organic, or biochemical species. It can reveal the form and the structure of molecules and their chemical information by measuring and analyzing the spectrum of light that is emitted, absorbed, or scattered by a substance. As an example, this molecule, which is composed of hydrogen, carbons, and nitrogen, can give us a specific absorption spectra as indicated on this diagram. For example, the hydrogen has its own specific spectra, absorption spectra at some specific wavelengths, which is around 438. The carbon, which is the black one, have also a different absorption spectra. Nitrogen have its own also absorption spectra. And when you see this molecule or this absorption spectrum, you can be able to identify what kind of molecular composition the sample has. So there are different types of spectroscopy techniques based on the type of radiative energy involved in the interaction. So the electromagnetic spectra used in spectroscopy encompasses a wide range of wavelengths and frequencies and energies, in which the visible region extends only from about 400 nanometer to 700 nanometer. So depending on the radiative energy involved in the interaction, we have different types of spectroscopic techniques. The known ones are the ultraviolet visible absorption, the infrared, and Raman. We have also different, which is different from optical range, which are the electron speaking resonance, nuclear magnetic resonance, or NMR, microwave, gamma, X-ray. The optical spectroscopic techniques include ultraviolet or visible spectrum, infrared, and Raman. They are under the optical spectroscopic techniques. And either bonding of electrons or rotational vibration of molecules could be the cause of the quantum transition and eventually the cause of absorption of light. So let's see optical spectroscopy specifically. And this optical spectroscopy is the general method for characterizing the optical properties of coatings, such as reflectance and transmittance in the region of the electromagnetic spectra. So these optical spectroscopic techniques utilize either the ultraviolet light or the visible spectrum or infrared radiation for visually identifying the elements in the sample that have been excited. So the procedure is the same. There is a light source, there is a diffraction grating or a prism, or it's called excitation monochromator. Then there is exit slit or filter that selects a specific wavelength of light, and that specific wavelength of light will be applied to the sample. The transmitted light will be again applied to the diffraction grating, because that specific wavelength light could be the cause of different wavelengths, because the molecule or the sample can scatter light, as either scattering or reflection or absorption could occur in that molecule, and there could be change in frequency. If there is a change in frequency, we could have different wavelengths light. So we may have light with a different wavelengths. So by using a diffraction grating, it's possible to separate that transmitted light into different wavelengths. Then we'll have exit slit to specifically select a specific wavelengths and analyze how much of that specific wavelength is absorbed in the molecule. So depending on the amount of absorption and the wavelength type, it's possible to identify the sample constituents or the concentration of the sample. The parameters, basic parameters that are used in spectroscopy, one is the Beer-Lambert law. The Beer-Lambert-Boger law relates the attenuation of light to the properties of the material through which the light is traveling. It characterizes the absorption properties of liquids or gases containing moderate quantities of a solid. This law is semi-quantitative. It can be used to measure the solid concentration using this equation. So the log of incident light divided by transmitted light can be related to the molar excitation coefficient, epsilon, the length of the solution, or the length that the light travels within the solution, times the concentration. So the length could be known in this case. Epsilon, the molar excitation coefficient, is known. The transmitted and emitted lights will be measured. The remaining will be the concentration. So concentration of the specific molecules can be calculated using this Beer-Lambert law. So transmittance and absorbance can be measured using this Beer-Lambert law. Transmittance can be calculated from the transmitted light divided by incident light, whereas absorbance is minus log of this transmittance. So this incident light intensity is known because you know what kind of light you apply to your molecule, and the detected light intensity also can be measured by different detectors. So the absorbance or transmittance of the molecule will give us a specific fingerprint for that molecule or unknown molecule. So how do you generate spectrum? Now we have seen how to calculate the concentration and how to calculate the transmittance, how to calculate the absorbance. A spectrum, there are two kinds of spectrums, continuous and band. Spectrum is just a salad of wavelengths that is used to determine qualitative properties. Spectrum, salad, slice, the slice of wavelengths. So the spectrum of incandescent solid is continuous because all wavelengths is present. Continuous spectrum. Band spectra, on the other hand, band spectra is the name given to groups of lines so closely spaced. Each group appears to be a band. Example, nitrogen spectra. This absorption or emission spectra have band spectra or group of lines closely spaced. So the continuous spectra, all wavelengths is present. In the case of band spectra, only a group of line spectra will present. So light spectrum in general is the collection of many different wavelengths of energy that are produced by a light source. So light is measured in nanometers. Each nanometer represents a wavelength of light or band of light energy. As an example, the visible light is part of a spectrum from around 380 nanometer to around 780 nanometer. So if we able to measure a specific wavelength of light, or if we have a specific wavelength of light, that means we are measuring a band spectrum or band spectrum. So we have also absorption spectra and emission spectra. The continuous spectrum, like that of white light, which is interrupted by dark lines or bands that result from the absorption of certain frequency of light by a substance through which the radiant energy passes, is called absorption spectra. It is a plot of absorbance as a function of wavelengths, or we call them Fraunhofer lines. Fraunhofer lines are set of spectral absorption lines named after a German physicist called Joseph Fraunhofer. The lines were originally observed as dark features in the optical spectrum of the sun. So the absorption spectra tells us the unique absorption wavelengths of molecules or elements. On the other hand, we have also the emission spectra, which is the spectra of the emitted light. The distribution of wavelengths in the light from the luminous source every element has its particular distinguishable pattern of electronic energy level, which is responsible for chemical properties and therefore emits its own characteristics collection of spectral lines that are observed when a species in excited state relax by giving off their excess energy as electromagnetic radiation. So the emitted light can be measured in terms of energy or wavelengths or frequency, and that is called emission spectra. A set of wavelengths that are emitted from a molecule when a molecule interacts with electromagnetic radiation such as light. We have the emission spectra, or set of wavelengths or set of frequencies. In the other case, the absorption spectra measures set of wavelengths that are absorbed by a molecule. So based on the amount of wavelengths or the type of wavelengths emitted or absorbed, we have mainly three types of optical spectroscopic techniques. These include the ultraviolet visible spectroscopy, the Raman spectroscopy, and the infrared spectroscopic technique. The ultraviolet visible spectroscopy or ultraviolet visible spectrophotometry, it refers to the absorption spectroscopy or reflectance spectroscopy in the part of the ultraviolet light and the full adjacent visible spectral regions. This means it uses light in the visible and adjacent ranges. All lights that are absorbed or emitted in the visible spectrum or in the ultraviolet region can be considered under ultraviolet visible spectrum absorption spectroscopy. It detects radiation associated with molecules within the electromagnetic spectrum that ranges 180 to 780 nanometers. These are more of the ultraviolet, and the 380 up to 780 nanometer includes the visible spectra. So the photon absorption arises from the transition of bonding electron or excitation from the ground state to one of the many vibrational and rotational energy states, which results in a shift of the absorption lines. So like we said, the absorption spectra can be plotted absorbance with respect to wavelengths. So if you see a maximum absorbance at some specific wavelengths, let's say 395 nanometer, with this absorption there is a specific molecule, because we have said that every molecule have its own absorption spectra. So the principle of UV visible spectroscopy is based on the absorption of ultraviolet light or visible light by chemical compounds. This results in the production of distinct spectra, which is called absorption spectra. So spectroscopy is based on the interaction of light with matter. So we need a light source, we need a matter or a sample that interacts with that light. So the UV visual absorption spectroscopy mainly contains a source, light source, filters, different kind of filters that selects a specific frequency, or set of mirrors. We have a sample, we have a detector. These are basic components. The radiation source, in the case of UV or visual spectroscopy, can be a tungsten or halogen lamp, or even better, deuterium lamp that serves to provide continuous light spectrum in the UV region. The other is the monochromator. In ultraviolet visual spectra, mostly diffraction grating or holographs can be used. This diffraction grating will disperse the light that comes from the tungsten halogen or the deuterium lamp. Then specific light will be applied after the filter selects specific frequency. Then there are detectors that measure the extinction in ultraviolet visual spectrum region. A photodiode can be used. Then after that photodiode, data processing can be used. For example, for retransform can be applied to see absorbance in terms of wavelengths. So this monochromator will disperse that light, and different wavelength light will be selected by this exit slit. A beam splitter can be applied that sends the applied light to the reference and the sample. The reference measures the incident light because there is nothing on the reference, whereas the sample or the photodiode on the sample side measures the output intensity I. So this data processing unit calculates the absorbance and plots it according to the wavelengths. This is called a spectroscopy. Absorption or absorbance with respect to wavelength is called a spectroscopy. And if the light applied and emitted is in the ultraviolet and visible spectrum region, it is called UV-VIS absorption spectroscopy. This is an example of UV-VIS absorption spectroscopy instrument. As you can see, the internal structure is composed of many reflecting mirrors, selectors, filters, different kinds of detectors, and the processing unit. You can attach a computer to this device to generate the absorption spectroscopy. So this UV-VIS absorption spectroscopy is applied for both qualitative and quantitative analysis. Usually, it is used in combination with other qualitative techniques to build up a picture that enables the absolute identification of unknown molecules. In the case of qualitative application, comparing the spectral plot with library data, a good approximation of the substance screen can be given. There is also only moderate absorption is the spectral wavelengths of light, which ranges between 200 and 800 or 700 nanometer. Aliphatic, certain alcohols, ethers, acid, and esters have different kinds of absorption spectra that helps us qualitatively identify what kind of molecular constituents exist on the sample. For example, aldehydes and ketones, they yield a narrow but specific peak at around 200 nanometer. So if you see high absorption spectra around 280 nanometer, you can guess as aldehydes or ketones exist on the sample. It can be used also for quantitative application. In order to achieve linearity between energy and concentration, highly monochromatic radiation should be used, which is grating with a narrow slit. So if you apply specific wavelengths of light, specific, let's say for example 400 nanometer light, this 400 nanometer light have a specific energy which is equivalent to h times the frequency. So identifying the energy or intensity on the other case, the incident intensity and output intensity, can help us identify concentration of the sample or molecule. So this way, it's possible to have quantitative identification of molecules, or the concentration determination is possible using spectroscopic techniques. As an example here, the spectrum of bicyclic diene shows some vibrational fine structure, but in general similar in appearance to that of isoprene molecule. So every molecule have its own specific absorption frequency. As you can see, for example, this molecule, which is indicated in pink, have its own unique absorption frequency. High absorption wavelength occurs at lower wavelengths, for example, for this specific molecule. For the other molecule, for this one, the maximum absorption occurs, for example, at this region. So like I said, every molecule has its own absorption frequency or absorption wavelengths, and that helps us to identify its existence on the sample. These are different absorption spectra for different molecules. The other technique is the infrared absorption spectroscopy. Infrared absorption spectroscopy, or sometimes called vibrational spectroscopy, involves the interaction of infrared radiation with matter. It covers a range of techniques, mostly based on absorption spectroscopy. This theory utilizes the concept that molecules tend to absorb specific frequencies of light that are characteristic of the corresponding structure of the molecules. So the energies are reliant on the shape of the molecules, the molecular surfaces, or the associated vibronic coupling, and the mass corresponding to the atoms. So infrared spectroscopy is applied on a molecule that possesses dipole moment. Any molecule possessing a dipole moment is IR sensitive, infrared sensitive. Dipole moment, it is a measure of polarity of chemical bonds within a molecule. It occurs whenever there is a separation of positive and negative charges. If there is separation of positive and negative charges in a molecule, that means the molecule have a dipole moment. So the vibrational and rotational absorption of IR frequency of the nuclei result in infrared spectrum, which shows closely spaced absorption peak resulting from transition among the various vibrational and rotational quantum levels of functional groups in the sample molecule. As an example, you can see the water molecule have some kind of dipole moment because of a separation of negative and positive charges. So this molecule has a dipole moment or possesses a dipole moment, so this is IR sensitive. This is IR sensitive. So when light in the range of infrared region is applied to this kind of molecules, the polarity or dipole moment could change for these molecules, or they will absorb some kind of vibrational energies or rotational energy levels, or change in the rotational or vibrational energies will occur in these molecules. So infrared is not useful in the determining quantitative measurement, but provide powerful tool for qualitative analysis. Since most molecular species absorb infrared radiation, except homonuclear molecules. Homonuclear molecules doesn't have a dipole moment. For example, oxygen, nitrogen, chlorine, they don't have a dipole moment because there is no positive and negative charge separation in this kind of homonuclear molecules. In the case of heteronuclear molecules that have different nucleus, for example H2O, 2 hydrogen and 1 oxygen, there is a dipole moment, and these kind of molecules are IR sensitive. So IR utilizes radiation spectra in the far infrared region, middle infrared region, and near infrared region bands. So it provides good data of the functional group present in the compound. So let's see how IR absorption occurs in these molecules that possess dipole moment. So IR absorption measures the energy of vibration of atomic nuclei in the molecule. In a 3 atomic molecule such as water, the stimulating incident light causes terminal appending atomic nuclei to oscillate around the centrally located atom. So there are two kinds of processes that occur when light in the infrared region interacts with a molecule that possesses dipole moment. One is called stretching and the other is called bending or in-plane bending. A stretching of bonds could occur when light interacts with molecules, or bonding of the molecules could occur when light interacts with this kind of molecules. So for IR absorption to occur, there should be asymmetric stretching vibration. If there is symmetrical stretching, there will be no change in the interatomic distance along the axis of the bond between atoms. But in the case of asymmetrical stretching, that means one will be stretched more and the other a little. There will be valence vibration. That means a change in the interatomic distance along the axis of the bond between atoms will occur. So one interatomic bond shortens while the other one stretches. On the other hand, the bending vibration, or called deformative vibration, are characterized by a change in the angle between two bonds. Change in angle between two bonds that will cause IR absorption, and that absorption can be detected. So in general, in IR spectroscopy, the bending and asymmetrical stretch vibrations are irrelevant, whereas the symmetrical stretch is not, because the dipole moment for symmetrical stretching, or the resulting change in dipole moment, will be 0 for symmetrical stretch. If the stretch is asymmetrical, there will be a dipole moment. If there is a dipole moment, IR will be absorbed. So only certain oscillations change the dipole moment, and only certain molecules are IR sensitive. So IR is one of the most powerful tools in the identification of pure organic and inorganic compounds. Usually a 2-beam infrared spectroscopy is used, and a tungsten lamp that radiates equally strong IR beams through the sample compartment and parallel aligned reference compartment is used. The instrumentation is the same: light source, there is a slit that selects specific frequency, there is a rotating disc, in this case specifically to select light of different frequency, one along the mirror and the reference direction, and the other to the sample direction. The light that comes from the sample and that comes from the reference cell will be compared on the detector, and the infrared absorption spectroscopy will be generated. So IR spectrophotometer most of the time uses a technique called Fourier transform infrared spectrometer. A photometer detects the difference in incoming radiation and feeds it to a monochromator, to the detecting device, and then a readout unit finally displays the wave numbers versus transmittance onto a screen or plotter. Modern IR spectrometers, like I said, uses Fourier transform instruments, the Michelson interferometer plus the Fourier transform will be applied on intensity of each frequency. So each frequencies will be taken simultaneously. So the FTR is usually used in the case of IR spectroscopy. So FTR, it stands for Fourier transform infrared, and it is the most common form of infrared spectroscopy. All infrared spectroscopics act on the principle that when infrared radiation passes through a sample, some of the radiation is absorbed. The radiation that passes through the sample will be recorded. And because different molecules with their different structures produce different spectra, the spectra can be used to identify and distinguish among different molecules. In this way, the spectra are like people's fingerprints or DNAs, or they are virtually unique for each molecule. This is a typical FTR spectroscopy. The principle is the same. There is light source, there are set of mirrors or beam splitters, there are detectors, there is analysis. The analysis converts the detected intensity or absorbance versus wavelengths to the infragram that converts to Fourier transform, and the spectrum will be generated. Different molecules have different intensities, absorption intensities, due to the stretching and bending properties of different molecules. There are different kinds of infrared absorption frequencies. As an example, the alkalines that range 2850 to 3000 per centimeter wave number. Wave number is the reciprocal of wavelengths with strong intensity. That includes these molecules with stretching vibration capabilities and ranges of intensities between 3050 to 4070 per centimeter wave number with medium intensity, can bend molecules, specifically CH2 and CH3. So a single molecule can have both stretching vibration and bending vibrations depending on its specific constituent molecules or parts. So this helps us to identify different molecules using their IR absorption frequency or wave numbers. So this FTR spectroscopy is used in organic synthesis, polymer science, petrochemical engineering, pharmaceutical industry, or food analysis. It has a wide array of applications, from monitoring processes to identifying compounds to determine components in a mixture. So this is a specific absorption spectroscopy for different molecules. For example, cyclobutanol have IR absorption spectroscope at this point. 2-butanol, for example, ethyl vinyl ether have different absorption spectroscopy. In this case, transmittance, we measure transmittance. So this is the inverted display of absorption. In the case of UV visible spectra, we measure absorbance, but in the case of infrared absorption spectroscopy, transmittance can be used. So the sample that did not absorb at all would record horizontal lines at 100% interpretance. So if a sample does not absorb any light, 100% transmittance could occur. But this indicates high absorption for specific molecules. The last one is the Raman spectroscopy. Raman spectroscopy is a spectroscopic technique based on inelastic scattering of monochromatic light, usually from a laser source. It is an alternative way to get information about the infrared transition within a molecule. In order for vibrational transition to be Raman active, the molecule must undergo a change in polarizability during the vibration. In the IR, we were interested about the stretching or asymmetrical stretching and bending of a molecule. But in the case of Raman, we are interested on the polarizability of the molecule. So polarizability refers to the ease of distorting electrons from their original position. The polarizability of molecules decreases with increasing electron density or increasing bond strength, decreasing bond length. So polarizability is a measure of how easily an electron cloud is distorted by electric field. Typically, the electron cloud will belong to an atom or a molecule or ion. So the electric field could be caused, for example, by electrode or a nearby cation or anion. So Raman spectroscopy uses this principle, the polarizability of molecules. The technique used to observe vibrational, rotational, and other low frequency modes in a system. So it is a result of inelastic scattering of photons of the analyte M dot. Inelastic scattering means there is absorption. So Raman is the most useful in the analysis of non-polar or hydrophobic and scarcely hydrophilic substances, which are IR inactive, or that doesn't have a dipole moment. Molecules that doesn't have a dipole moment can be polarizable, and that they can be detected by Raman. For example, the vibration in nitrogen is not IR sensitive because it doesn't have a dipole moment, but it is Raman active because only the polarizability of the molecule is changed during nitrogen-nitrogen vibration. The delocalized electrons interact with the oscillating electromagnetic field. So this interaction of delocalized electrons from nitrogen-nitrogen bond with the oscillating electromagnetic field that comes from applied light makes the nitrogen Raman active, but it is not IR active because it doesn't have a dipole moment. The dipole moment for nitrogen is 0. So Raman spectroscopy uses the Stokes shift and Stokes and anti-Stokes shifts principle. The scattered radiation is termed as Stokes and anti-Stokes. Emission peaks due to inelastic scattering differ in wavelengths of the excitation frequency and Rayleigh elastic scattering. So the Stokes or Raman peak with identical patterns are found in either side of the Rayleigh peak. So just to revise what we have said in the previous classes, when light gets absorbed by a molecule, it will emit equivalent light with equivalent frequency. That's called Rayleigh scattering or elastic scattering. If there is elastic scattering, there is no frequency change and there is no energy loss. This is called Rayleigh scattering. On the other hand, the electron that is ejected to a higher state could return to the ground state by releasing light with small frequency or less energy. That's called Stokes-Raman scattering. Stokes-Raman scattering. On the other hand, if an electron with different vibrational energy state in the ground state is ejected to a higher energy state, and when it returns to the ground state, if it returns at different vibrational energy state on the ground, anti-Stokes-Raman scattering could occur. That anti-Stokes-Raman scattering results a photon with higher energy. a photon with higher energy. So we have a Stokes, which is a small frequency, Rayleigh equivalent frequency or elastic scattering, and anti-Stokes, which is higher frequency. This is the emitter light. So the anti-Stokes lines is much less intense than the Stokes lines. This is because only molecules that are vibrationally excited prior to irradiation can give rise to anti-Stokes. If the molecules are not vibrating on the ground state, the anti-Stokes Raman scattering will not occur. The energy difference between this Rayleigh and Stokes reveals the frequency of the vibration of the molecular species on the ground state. As you can see, Rayleigh results on the same vibrational energy state, whereas the Stokes, when an electron returns to the ground state, it could stay on different vibrational energy states on the ground, and this difference, the difference energy, is called the Stokes energy or Stokes frequency. The frequency between Rayleigh and the returning Stokes emission is called a Stokes energy. That is a change in energy, change in V, change in frequency, which results change in energy. So Raman spectroscopy uses these Stokes shifts, and the instrumentation is the same. As Raman spectra are incredibly weak signals, there is a small shift between the Rayleigh and the Stokes, so the signal is very weak. Raman spectroscopy is the result of vibrational energy modes of molecules, and the signal detected is very weak. The signal is due to the vibration, not due to excitation or emission of molecules. It is due to the vibration of molecules. The vibration energy change will be measured in the case of Raman spectroscopy. So they are best obtained by irradiating a sample with powerful laser source of visible infrared monochromatic radiation. So during irradiation, the spectrum of the scattered radiation is measured at some angle, usually perpendicular with a spectrophotometer. So at the end of the signal processing path, the readout device displays the emitted Stokes peaks versus wave number. So as an example, a laser source is needed to excite the target species. Then a filter or the dichroic mirror collects the Raman scattered light or Stokes and filters out the Rayleigh and anti-Stokes light. This laser light will be applied to the sample. The reflected light, the scattered light from the sample, will be collected on the dichroic mirror, and this dichroic mirror or filter will select only the Stokes, which has less frequency or less energy, and passes the others. High energies will be passed because we are interested on the Stokes only. Then the beam splitter sends the Raman scattered light into the fixed mirror and the moving mirror. That means Michelson interferometer technique will be used. If you have fixed mirror and moving mirror, the Michelson interferometer principle will be used. Then a detector records the signal and passes the signal to a computer for decoding. Fourier transform can be applied to see a specific wavelength absorption or Stokes absorption. That will be displayed on the display device, which will give us information about the molecular fingerprint of a substance or a sample. So Raman spectroscopy is both qualitative and quantitative. The general spectrum profile, which is a peak position and relative peak intensity, provides unique chemical fingerprint which can be used to identify a material and distinguish it from others. Raman spectra of ethanol and methanol, for example, as you can see on this picture, they show significant spectral difference that allows us to identify the two liquids, to distinguish the two liquids. Ethanol, for example, have a specific absorption or Raman spectra, which is different from methanol. That helps us to distinguish these two liquids. Quantitative analysis, similarly as in the case of infrared spectroscopy, peak intensities can be utilized to measure the species intensity by comparing it to a series of standard reference solutions. This allows us to do quantitative analysis. So to see the difference between Raman and IR spectroscopy, Raman spectroscopy is a complementary technique to infrared spectroscopy. Both examine changes in vibrational rotation at a molecular level. But while infrared measures the amount of IR light absorbed, Raman measures the amount of light scattered. So the two techniques are complementary in that they can tell you different things about a molecule. So Raman spectroscopy depends on a change in polarizability, whereas IR spectroscopy depends on change in the dipole movement. So Raman measures relative frequencies at which a sample scatters radiation, whereas IR measures absolute frequencies at which a sample absorbs. So transmittance is measured in the case of IR. Intensity of the scattered light will be measured in the case of Raman. That intensity of scattered light is the Stokes light. The Stokes light that comes due to vibrational energy changes. That was all about this section and all about this course.